Good afternoon. Thanks for coming. And welcome to the third talk of the MIT.nano Perspectives in Nanotechnology seminar series. So it is my great pleasure to introduce our speaker today, Professor Eli Yablonovitch from UC Berkeley. Eli has contributed tremendously to many fields, including introducing the idea of strained semiconductor lasers, photonic crystals, and many contributions to development of high-efficiency solar cells. Eli's work has also significantly contributed to commercial applications, leading to many multiple companies. So Eli is an elected member of the National Academy of Sciences, the National Academy of Inventors, the National Academy of Engineering, as well as the American Academy of Arts and Sciences, and a foreign member of the Royal Society of London. So Eli has been recognized by many prestigious awards and recognitions, amongst which is the IEEE Edison Medal, the IEEE William Cherry Medal, as well as the Isaac Newton Medal, and many, many, many more. But I'll stop here and invite Eli to join me here on the stage so that he can give us his perspective on what new device will replace the transistor. So please help me welcome Eli.
Wow, that was a great introduction, Farnaz. I don't think I'm going to live up to it. I'm just really a regular guy. and we're facing kind of a problem that just we're all sort of confronting. It is that the transistor is getting very, very old. It's actually 1 year younger than me. That gives you an idea how old it is. And you've got to figure there's got to be some improvement that we could possibly come up with. Something new. And so the first I'll describe where there is possible room for improvement, because maybe it's just a terrific device and we can never improve it. But let's first of all define the problem. We have integrated circuits like this. We have transistors down at the bottom. They drive all the wires. But the reality is that, and this is of course a very old picture, and things have been substantially miniaturized since then, but the parameter of miniaturization, we're running out of it because the transistors are hardly bigger than molecules now. So either progress comes to an end or we come up with something new. So the question is, what can we possibly come up with that's new that would represent a meaningful improvement now that we've completed the course of miniaturization? This is also represented on this graph, which I got from my colleague at Berkeley, Dave Patterson, who is a computer scientist, and he's looking at all of the improvements. I guess for him, life began in 1980, and he's famous for RISC, but then we had the end of Moore's law scaling. We're not quite the end yet. And then there was a brief period when people believed in the Amdahl's law. And finally, it seems like things have leveled off. This slide is already a couple of years old. So you can see something has already happened for the computer scientists that they have plenty to work on. Well, what has happened for them is the emergence of neuromorphic computing finally the neural networks. So the neural networks go way back, especially here at MIT. There was great interest and hope for artificial intelligence in the 1950s, and it didn't quite work out, but they should have just kept at it, because later on it became very successful. Later on, meaning let's say around 2012, neural networks finally became successful, and they were doing amazing things like recognizing images, interpreting X-rays. Oh, by the way, I just noticed there are a lot of people standing in the back. Now, I want to assure you, this talk is not going to be good enough that you want to stand for the whole talk. There are, however, some seats up front, and so some of you should take the opportunity of resting your legs and coming up front. Okay, and for the rest of you, go to a neighboring room and get a chair. There are two more seats. Okay. All right. So what happened in 2012 is that by applying enough resources and enough training material, namely all the images in the YouTube database, And by inserting it, finally neural networks were successful, and it has become a very big thing. It was thought to be a gigantic breakthrough in computer science, which it is, but then by 2015 it was realized that the main requirement for neuromorphic computing is linear algebra. And so in 2015 the idea emerged that, oh, we need specialized hardware which is just dedicated toward linear algebra. And that was the period that we're in now, which is the period of hardware accelerators. And the hardware accelerators are coming in various forms, digital forms. You have analog machines or analog circuits which can do matrix multiplication, which is like analog, oh my God. Of course, the digital people think that's all crazy. But then here at MIT, you've gone one step beyond analog, you've gone photonic analog, because there are a beam splitter in photonics is a 2x2 matrix multiplier. And if you put many beam splitters together, you can do matrix multiplication. So we are living now in the era of hardware accelerators and the re-emergence of hardware as being very important. And the computational part, yeah, you could probably learn that in about a day. It involves a certain amount of linear algebra. And so the CS part was relatively easy, but the hardware accelerators are going to keep hardware going for quite a long time to come. Now, of course, all this artificial intelligence is a fantastic thing. It has not displaced normal computing, and it is a major complement to normal von Neumann architecture. And so this is the biggest supercomputer as of last year, and it is located at Oak Ridge National Labs called Summit, and it is about half a normal supercomputer, and the other half is all neural network, let's say accelerators or processors, or basically means linear algebra. So all future supercomputers are going to be half normal supercomputer and half would be neuromorphic architecture, which is basically running some algorithms that require a heavy dose of linear algebra. So this is the biggest thing happening right now, and it has tremendous legs. Some people think it's going to go on for a couple of decades. The people in this field think this is bigger than the internet. But it may be, but it's a little bit slower than the internet, so it's going to take a couple of decades to work out. But one thing for sure, that they still run on transistors. And so we still have a question ahead of us, and that is, are we going to stick with the transistor that is presently 70 years old, or are we going to come up with something better? So I show here a picture of a transistor, and basically what you have is you have electrons. Let's say you have electrons, and they're going from between two contacts, a source and a drain. The electrons are traveling along. They're minding their own business, but they're running into all these negative charges, which produce a potential barrier. So you have the gate, you put a negative voltage on the gate, and this repels the electrons. So for the electrons to complete the circuit, they have to go over a potential barrier. And that's the way a normal transistor works today. But it's also the way all the modern concepts, like a carbon nanotube transistor, works the same way. A potential barrier, and you have to surmount the potential barrier higher. Okay, and that's sort of universal. And so let's see if that gives us an opportunity to invent something better. So let's sort of describe what I just said, is that you have electrons, and they're jumping over this potential barrier, like that. And we want to turn the transistor off. We simply raise the barrier. Now, the problem with this concept, this is a universal concept in all types of transistors, is that what turns the current off is the Boltzmann factor. So it said, well, okay, fine. If I raise the barrier high enough, that will turn it off. But then you actually have to raise the barrier quite high, because you really want, when you turn a transistor off, and I'll say this a couple of times, when you turn a transistor off, you really want it to be off. And the reason is that most of the time the transistor is doing nothing. It's just waiting. For example, on a keyboard, let's say it's connected to the transistor connected to the Q letter on the keyboard. Well, you don't use Q very often. So the transistor is sitting around a lot. And so you need to, when you turn it off, you don't want to be leaking current while it's waiting. And so you end up with your Boltzmann factor, you need at least about 0.3 of a volt just to deal with the Boltzmann factor. You want to turn it off by a factor of 1,000,000. 1,000,000 is roughly, let's say, e to the minus 12. And then e to the minus 12 means the voltage has to be 12 times kT. KT is, the thermal voltage is 25 millivolts, and 12 times is 0.3 of a volt. So it says at minimum you need 0.3 of a volt to turn your transistor off. Okay. Otherwise it sits there and leaks energy, so you don't want that. And that's what they do. But really it's not 0.3 of a volt, it's more than that. For example, there's inefficiency in the gate. There's a lack of reproducibility from transistor to transistor, and so you have to put in a little extra voltage. So when it comes down to it, what happened about 15 years ago, the voltages, they kept reducing the voltage, they kept making progress, but they stopped improving the voltage much at all. So about 15 years ago, if you bought a laptop, the voltage would be 1 volt. And if you bought a recent laptop, the voltage would be 0.9 of a volt. So there's almost no progress because you're fighting the Boltzmann factor, okay? And so the first thing you need to do is that you need to defeat the Boltzmann factor. Now when so I'm here partly representing the E3S Center, and when I wrote the proposal, one of the referees wrote back as a referee's report and said, these people are very presumptuous. Who are they to defeat Boltzmann? Okay, and to defy the Boltzmann factor. So fortunately, I had an answer for that, and so we did get funded. But what do we need? To defeat the Boltzmann factor means we need to make the transistor more sensitive. We don't want to be limited by kT. So if this is a normal transistor, which maybe it's a very good one that we don't quite have yet today, and it takes 0.3 of a volt to turn it on and off, we simply want it to be more sensitive. So that's very easy to understand. If it's more sensitive, then the response is more like a step function. And if it's more like a step function, you don't have to supply as high a voltage. And so you ask, well, how low can you go in voltage? Well, presently, we're close to 1 volt. Maybe we're 0.9 or 0.8 of a volt. How far can you go? Well, we can probably safely go to 10 millivolts because noise in electronic circuits, if you've ever used an oscilloscope, it gets noisy below 1 millivolt. So you have 10 millivolts, you have adequate signal-to-noise ratio. That means you could reduce, this is the elevator pitch, by the way. You could reduce the voltage by a factor of 100, okay, that sounds pretty good. Factor of 100 reduction in voltage, but then the energy is reduced by voltage squared. Now you're reducing the power by 10,000. Now that gets to be very attractive because at 10,000, wow, that's like many decades of Moore's law, the new Moore's law, the one related to energy, the one that we don't have yet. So the goal then would be to find a new device that is more sensitive. If it's more sensitive, it won't need as much voltage. We'll reduce the powering voltage, and we'll use 1/10,000th of the amount of power that is normally needed. So that's the payoff. That was the elevator pitch. And in effect, this is more or less what I said. It's the same thing as on the previous slide. This 60 millivolts per decade, this is a way of saying the Boltzmann factor because engineers like to do factors of 10. Physicists like to use factors of E. So in E would be a voltage over 25 millivolts. And 60 millivolts is for factor 10. 25 millivolts is for a factor E. So this is like your normal good transistor right here. But we want to be better. So we want it to be steeper. Now the way it works in this field, if you are more sensitive, like instead of 60 millivolts per decade, you have 55 millivolts per decade, you can publish that in any the top journal right away because even slight improvements are regarded as totally amazing. Of course, some of them don't work out, but we're not interested in going from 60 to 50. We want to go all the way down to where it's really a sharp turn on, and maybe we can operate the whole circuit for only 10 millivolts of powering voltage. That would be fantastic. So that's what the goal is. Now, I have a viewpoint about transistor that's a little different. Many people think of the transistor as a switch. It is a switch, but I think of it as a communications device because the purpose of the transistor is to send current down these wires or voltage down these wires. So this is an old integrated circuit, and it just shows that it's all about sending the current down the wires. And what is a transistor for? It's a communication device. Sometimes you're only communicating 10 microns on chip, but it's still a big investment of energy. And the transistor is providing that voltage. So I think of the transistor as a communications device. If I can communicate at 1 volt, that's where we are today. But if I can send signals at 10 millivolts and get the same quality of communication, then I save energy by a factor of 10,000. So it's worth doing. So that's one thing we want. We want the transistor to be more sensitive. Now I have here 3 things we want from a transistor before we can declare success. Let's say we have some kind of concept that we make it more sensitive and we use these log to the base 10 units, so it's millivolts per decade. Then I already hinted that there was another requirement. When we turn it off, it had better be off because we don't want a lot of leakage. And so more or less 1,000,000 to 1, the computer architects have sort of figured this out. And yeah, 1,000,000 to 1 is probably a good enough turn off. And then there's a final requirement. It took me actually a long time before I understood why this was such a big requirement. But the industry insisted upon it. I finally figured out why. The industry said that you have to supply 1 milliamp per micron of size of transistor. And I couldn't quite figure it out, but one thing I knew is that it shouldn't be a milliamp, it should be a millisiemens, because a milliamp would be at 1 volt, which is where they are today. If we succeed somehow in lowering the voltage, we will also be lowering the current. And so we shouldn't express the figure of merit as current. We shouldn't say milliamps, we should say millisiemens. And we need to have enough conductivity. So the transistor has to have enough conductivity to provide basically a millisiemens is like 1,000 ohms of resistance when it's on. Okay, so but in a small, obviously make the transistor bigger, you'll get more current. So it's per micron. Okay, so why that last requirement? So I have here a picture of a modern chip, and there are actually 14 levels of metal. And you can only see it up to number 12, and you go down, and way down here at the bottom are the transistors. You can barely see that at the bottom. And there's actually 2 more layers that don't even fit. And so you can see that the transistor has a very difficult job because it has to drive all the capacitance of all of that wiring. And since you only have 1 layer of transistors at the bottom and it has to drive 14 layers of wiring, it has to be able to deliver a lot of current or a lot of conductance, because otherwise your chip will be too slow and no one will buy it. Okay, if you can't deliver the current fast enough, you can't turn the wires on and off fast enough. So you need to have the ability to deliver a lot of current. And that becomes yet a 3rd constraint. Of course, there are many more constraints like manufacturability and so forth, but these are the main things. These 3 are the main things you want to achieve: sensitivity, on-off ratio, and you simply have to be able to deliver a lot of conductivity, which is kind of tough. Okay, so those are the 3 things. If you have a great invention and all it does, it gives you sensitivity, it won't be enough. And you have to provide the other 3 things at a minimum. Okay, so that's our challenge, and it is a worthwhile challenge because if we do it, then we gain 4 orders of magnitude. So this is where we are today. And theoretically, if we just deal with noise, we could be 10,000 times lower current. This noise limit was originally worked out by a theorist at Rolf Landauer. I've come to realize that I'm so old that I actually was friends with these people, okay? And because he's sort of a legend among his many accomplishments, he figured out what is the energy cost of computing. A very interesting character. But his prediction is we're still 10,000, 100,000 times, 1,000,000 times away from his predictions. So I started the Energy Efficient Electronic Science Center, and I put a team together. I selected the best professors I could find in the whole country, and naturally you see a great many of them are from MIT. Okay, and it's been very successful, and I'm very happy about our collaboration. So we've been working at this, and it's kind of hard because you have to sort of invent new things. And by the way, any of you can invent new things, because I can tell you we haven't solved the problem yet. So that means there's room for any one of you to come up with an idea. It says, boom, that's the idea. And that's the one that's going to change the world. So let's just see what ideas we did come up with. First of all, what is it good for? Is that, of course, I don't have to tell everyone that it's everywhere. It's in the infrastructural core, meaning data centers. It's obviously in my cell phone, in your cell phone. It's in network sensors, and most importantly, body-centered networks. And I just realized that I have 2 watches that are monitoring me, monitoring my pulse and so forth. This is going to be normal. There's a lot of research going on how doctors can use continuous monitoring. And I got into arguments with venture capitalists. They said only sick people need that. And I said, no. Wealthy, healthy people need that because they want to live forever, those wealthy people. And they're going to say, in the future, instead of freezing myself, I collect all the data. In the future, doctors will be able to interpret it, and it'll help my medical care. So all of these things are coming on. The 3 at the bottom are portable, so they're battery operated. So you know that energy is very important there. But also in data centers, energy is very, very important. And artificial intelligence, yes, there's more and more we can do. And that's sort of in between, because they want some of the artificial intelligence. For example, this is coming to a phone near you, is language translation and language interpretation, the voice interpretation. So that obviously would require battery power. So we need very little energy consumption. So we need to come up with some new type of switch. Now the transistor is a kind of a switch. And so what are some of the ideas? Well, there's an idea of maybe being able to do something with normal semiconductors. Wouldn't that be great? We just make a different device in semiconductors, and one of the devices that looks very promising is the Tunnel Fet. Of course, on the nanoscale, everything becomes tunneling anyway. So if we do that, that would be terrific, because maybe we can just drop it in, replace the normal transistor, and it will be accepted right away. But that's, you'll see soon that that's very hard. We're very far away from that. There are other types of switches. There is room for nanomechanical switches. And I'll show you that in the center we were doing some work with nanomechanical switches. I'll be featuring the work of your own Professor Farnaz Nirui. Okay, and then people say, oh, we can switch magnets. Now this looked like a long shot, but just in the past few years, there have been new discoveries in magnetism where you can switch a magnet with ever less current. So there's now something called spin orbit torque, where you have you have a microamp, and you can switch a magnet. You just switch a magnet. You can turn that into a resistor through a magnetoresistor, and I'll show you an example of that. And then there are some people who say, well, that's all to drive wires. I don't need wires. I have silicon photonics now, and maybe I can replace at least some of the wires with photonics, and is there some new way of doing very low energy optical communication? So these are the different approaches, and I'll show you quickly a little bit of each, and then I'll focus in on the main thing. I want a drop-in replacement for the transistor. I want something made of a semiconductor. I can just put it in and replaces the transistor. Let's see if that's possible. That's what the highlight of the talk is going to be. So first of all, how do we beat the Boltzmann factor? So it is, I'm going to give you the secret right now, how to beat the Boltzmann factor. Okay, suppose you have a conduction valence band like this, and they're quantized, they're small. And so I have a valence band level, and I have a conduction band level, and they're perfectly lined up, and current flows. There's a little arrow. I hope you can see the arrow. The current flows, and everything is fine. Okay? And then what I do is I misalign the 2 energy levels, and now the current has no place to go. Okay? So just by this expedient, let me show it to you again. That's off, on, off, on. That's my new switch, no Boltzmann factor. Now you can say, oh, wait a minute, there's a Boltzmann factor up here, and there's a Boltzmann factor down here for the holes. Yeah, but what matters is the alignment of the 2 levels. There's no Boltzmann factor down in the band edge. So this assumes that the band edge of the semiconductor is very sharp, and this allows us then to defeat the Boltzmann factor. There's no states here, so there's no Boltzmann factor to worry about. So this is the way that we're hoping to defeat the Boltzmann factor if we make a transistor based on this principle. And this principle is called the tunnel field effect transistor. So it's hard. Let's look at some of the other options. What about nanomechanical switching? Well, these are some slides I got from Farnaz Nurui, and you can see what's going on. It looks very much like a field effect transistor. It has gates. In this case, it has 2 gates, has a source and a drain. Now, normally, what would happen is that you would have a vacuum gap. So this is how nanomechanics has generally been done. You have a vacuum gap, but you get into all sorts of problems, and the 2 metals end up sticking together and so forth. So what Farnaz did is she invented this thing where it's called a switch. So you put, instead of vacuum, you put a molecule in here, and as you squeeze the molecule, you finally bring the electrodes closer together, and by the time they're within about 3 nanometers, current starts to flow. And so you never allow the metals to touch, and so you switch it down like this, and now the current is flowing. The metals don't touch, and they don't stick together, and it's good. And this is an example of an IV curve that she has. And so she is still the leader in this field, and it is very promising. Not necessarily to be an exact one-to-one replacement, but for specific applications. For example, in the Internet of Things, you want to do the biggest energy cost is you have to radio out the data. And if you can compress the data before you radio it out, but you need to have very low standby power. So this is fantastic. Maybe once a day you radio out the data, and but you do the pre-processing, the digital compression. You do it with a circuit like this. Might require only 1 or 2,000 of these mechanical switches. So it's a very interesting application. Okay, and that gives you an idea of how sharp it is. It's not 10 millivolts, but it's pretty good. And this is a picture of her actual device, where these are the control electrodes. This is the source and drain. And you get the tunneling current coming through this rod. Very interesting. Okay, what about nanophotonics? Just trying to figure out what's going on. And the idea, we have now silicon photonics is a real thing, but it's always done for long distance communication, maybe 100 meters or more. Maybe a little bit less than that, but if you're going on chip, you can't, the idea of having a laser would be kind of crazy. It's too much baggage with a laser. So we have the idea of having an LED as the light source. We need a very sensitive photodetector, but then how do you make an LED competitive with a laser? And so the idea that we've been pursuing is that, and this is an idea which is sort of like 120 years old, is that Heinrich Hertz, actually 130 now. Heinrich Hertz discovers radio. Heinrich Hertz invents the radio antenna. And then radio develops, and we have radio antennas. And without it, you can't, radio would be useless. You need to have it. For some reason, it took 100 years to realize that we could do antennas in optics too. And it could be very helpful. For example, in a light-emitting diode, you get light out faster. Just like the same benefit as in your cell phone, is you need the antenna to get the signal out faster. So we have this idea of antenna-enhanced light-emitting diodes. We've actually made them, and they are competitive with lasers. Right now, they're at the same speed as lasers. They can be 50 gigabits or so, and it's basically an optical antenna. So, hey, there's something to be learned there. Okay, and here I show what the actual antenna looks like. It is more of this type of structure. By the way, anything can be an antenna. I teach the electromagnetics course at Berkeley, and in the first class I say anything can be an antenna. a chair, a metallic chair. Oh, each of you can be antennas too. Okay, and then I challenge the students, what's your resonant frequency? And then it goes on from there. Okay, so that's optical, but it only fulfills some of the requirements. It doesn't really fulfill all of the requirements. Certainly you wouldn't want to use photonics for very short links. So longer links maybe. Okay, so then we come to another interesting piece of physics that was really spurred on by the spin-orbit torque, which is an idea that you can send current along an ordinary metallic wire, non-magnetic wire, and yet there will be magnetism created on the surface, because at the surface you have an electric field holding the electrons into the wire. And so when the electrons are tangential to an electric field like that, there is a spin orbit effect at the surface of normal metals. It's kind of amazing. And it was, I don't know when it was first discovered, but it first came to everybody's attention about 7 or 8 years ago. And so this leads to a concept that is kind of interesting. First, I'll mention what my colleague, Professor Jeff Boker, he has discovered that you can do a very rapid electrolysis, because if you're going to do this, you need to switch the magnets very rapidly, and he found out that you could electrically switch a magnet. Now, normally it would be limited by the precession frequency, which is about 10 gigabits, and you can go down to terabit of speed. And the mechanism is more or less that you quench the magnet. So you supply electrical energy. It sort of heats up the electron gas. It gets quenched. And when the quenching goes away, the magnet reemerges with the opposite polarity. And there's actually a very strange alloy that has this property. It toggles back and forth. And so this is the fastest switching of a magnet. And so it's, okay, that's useful. But how are we going to use it in a system? Let's just see, where are we going? Okay, I have to go back. Oh, I'm missing a slide. Oh, it always happens. So the slide that I'm missing is how you're going to use this. And the way you're going to use this is you switch the magnet. The magnet switches a magnetoresistor. So you have a magnetoresistor in every hard disk as a magnetic field sensor. The magnetoresistor, you apply a bias voltage so you get current. And that current drives the next spin orbit torque switch. And so you have essentially an electrical device, current in, current out. And inside the black box, inside the transistor, is a magnetoresistor and one of these spin orbit torque switches. So it's still electrical wires. I don't think we're ever going to get rid of the wires in a chip, but we have another way of switching. Now, it will be terrific except for one little problem with the magnetoresistor, the on-off ratio. We have magnetoresistance. How do you like 2 to 1? That was fantastic. That was once called giant magnetoresistance. Well, we need 10 to the 6 to 1, so it's not there. So we can do a lot of things. There might be some specialized applications, but it's not necessarily going to be a 1-to-1 replacement for the transistor, but very interesting physics nonetheless. So with that buildup, say, okay, we want the whole thing. We want everything. We want a 1-to-1 replacement for the transistor. We want it to be made out of semiconductors, and how are we going to do that? So I already told you, is that we're going to do tunneling. Well, the tunneling is not that critical. What we're really doing is lining up 2 energy levels and then misaligning them, and that's it. And we've defeated the Boltzmann factor and potentially a very sensitive device. Okay, so what's the problem? So on the left side of this slide, I have our imagination. In our imagination, we have a sharp energy level in a semiconductor. It's a quantum dot. We have another sharp energy level. We tunnel from one to the other, and the switch is perfect. Okay. In reality, we never get sharp energy levels. So we're starting now to think a little bit outside the box of normal electronics. Now we're talking about how sharp are the energy levels. So we're talking a little bit about spectroscopy. So I have my energy levels, but now I'm a little more realistic on the right-hand side. Yeah, there's going to be some line shape. Now, why would there be line shape? Well, there are a lot of reasons, but let me show you the bad thing that happens. Then on the conduction band side, we're empty state, so it's going to receive the electrons. you also have some kind of funny line shape. And like every spectral line, it has a tail. And so you're supposed to be in the off state because the levels are misaligned. But wait a minute, I've got a tail. I still have a little bit of current here, and I have a little bit of density of states here, and I can't turn the device off. That becomes one of the many problems you have to solve. How do you turn the device off? You say, well, that's easy. You just make the spectral line sharp. So oops, it's really hard to make a sharp spectral line. And there hasn't been that much theory on it. And although it is kind of a famous problem in theoretical physics, is predict the spectral shape of some spectral line. And it's actually quite hard. So I went to, we have a very outstanding theoretical physicist at Berkeley, Steve Louie, and I said, Steve, I'm very interested in actual spectral line shapes in solid state. And you're an electronic structure guy. Can you tell me what spectral line shape to expect? He says, well, you should expect a Lorentzian. And you can go to many theoretical physicists, and they will all say, of course, it's Lorentzian. Every spectral line is Lorentzian. So let's ask what happens. Now you're interacting. Now the spectral line is interacting with a contact because I didn't show it, but I think I'll show it. Here it is. You have your quantum dot. It has to be connected to a wire. So you have many things that could broaden. So you have a sharp level. And you say, well, there are a lot of things that, there's disturbances all over. But the biggest disturbance is you've got to connect a wire to it. So the electron cannot stay on the quantum dot very long. It has to go into the wire and be collected. And so that's going to contribute to the line width. But all the other things are also going to contribute to the line width. So let's try to figure out how we could possibly get the line width sharp enough to make a tunnel FET successful. So here's the naive thing that the physicists all believe. They believe in Fermi's golden rule that says if you put an electron on the quantum dot, it's going to decay away according to an exponential law, which is with a fixed probability per unit time, and it decays away. Now, I am moderately good at math. I can do a Fourier transform of that function, and if I Fourier transform that function, I get this line shape, which has a very famous name. It's called Lorentzian line shape. And if I truly had Lorentzian line shape, which is the most common assumption, I'd be dead already. I mean, it wouldn't work at all. And let me show you why. The Lorentzian line shape, it falls off as 1 over energy squared, or let's say omega squared. That's a slow algebraic fall off. So I have my line that has a certain shape, and Lorentzian is very broad. It's probably the broadest line shape you could imagine. And then I'm going to have leakage and say, oh, look at this. And yep, I got a big density. I can't turn this device off. Okay, I try to turn it off, but this is the density of states is just falling off much too slowly. So it's hopeless. So if you were truly a believer in Lorentzian line shapes, which my experience is that most physicists believe in it, you might as well give up on the tunnel FET. So there had better be some way to solve that. Now, if you could solve it, it would be like the blue curve. And the blue curve, the spectral tails would fall off very rapidly. In fact, they fall off exponentially. That is the usual assumption in tunnel FETs, is that you get this exponential fall off. And then when you turn it off, it falls off exponentially and everybody's happy. And that becomes the figure of merit of the tunnel FET, is usually expressed, and I think I showed this already, in millivolts per decade. So that's essentially a statement that it falls off exponentially. Millivolts per decade is in effect assuming the blue curve works. That's the figure of merit. And of course, nobody has done well on this. People publish if they have like 57 millivolts per decade. That's like a big publication. So they're really having trouble getting past 60. Okay, and 60 is Boltzmann factor. So you can't turn it off if you believe in Lorentzians. So like it or not, electronics has to start studying spectroscopy. Okay, and this slide just shows the same thing when Fourier analyzing the Lorentzian and Fourier analyzing another function which is much better, which I'll show you in just a minute. So the TFET concept would fail if spectral line shapes were Lorentzian. So we better hope there's something else. So how does it fail? So it fails because it doesn't turn off fast enough. So you will never get the millivolts per decade. In fact, it'll fall off as inverse square, which is really a very slow fall off. And because the fall off is very slow, you're going to never turn it off. So you'll lose on the on-off ratio. So 2 out of the 3 things you need to achieve are impossible if you believe in Lorentzian line shapes. So what is the reality? So now we first have to defy the Boltzmann factor. And if we believe in Fermi's golden rule, we get the Lorentzian line shape. So we now have to defy Fermi's golden rule. So here I have a more detailed close-up view of the decay of, let's say you put an electron on a quantum dot, how rapidly does it decay? How does it decay into the wire? And if I believe in Fermi's golden rule, it's the red curve, okay? But there is a slight problem in Fermi's golden rule, which I will show you in a minute, and that suggests it doesn't start right away. There's a little bit of a delay, and that delay I'm expressing with a second lifetime. So it says, yeah, Fermi's golden rule is good, but it has 1 lifetime. We need a second lifetime. There's a small period at the beginning of every exponential decay. There's a small period in which it's not exponential. In fact, it's quadratic. It's falling off as a square. And then gradually it becomes the normal Fermi's golden rule. So we are saying that Fermi's golden rule is incomplete. How many people learned Fermi's golden rule? Just about everybody gets it because everybody took a quantum mechanics course. So I don't think I'm exaggerating to say you were taught that you get a fixed rate, okay? And I was taught the same thing, but not quite, not quite.
I was taught there are a lot of assumptions.
Exactly. There are a lot of assumptions. It is perturbation theory. There are a lot of assumptions. So now we need to dig a little bit deeper, okay? And if we dig a little deeper, we find out that there's too many assumptions. And realistically, you have an initial parabolic period. Now, if you then say, okay, that's great, you have initial parabolic period, what does that do to my spectral shape? So I go and I look at my spectral shape, and the middle of the spectral line looks pretty much the same as always. And that's determined by the Fermi's golden rule time decay. But if I allow for that initial period where something different is going on, that very short times correspond to very big frequency shifts. And so way out in the tail of the spectrum, where nobody ever looks, that little induction time gives you that steep fall off that we're looking for. So Lorentzian is bad, but the blue curve, it includes that initial parabolic behavior. And what I'm saying in effect is if you learn the Fermi's golden rule, it's somewhat incomplete. And in fact, if you did it more correctly, there would be 2 lifetimes. There's a familiar lifetime that you're familiar with, and there's this little induction period at short times that you need to be aware of, and that everybody ignores. Almost everybody. So if you go through your quantum mechanics books, it's mostly ignored. But here is a book by one of the more brilliant people, Kohn Tanuji, okay? And he is famous for his quantum mechanics textbooks. He's a true master. He's an atomic physicist, a true master of quantum mechanics, and also a very careful person. So he's very careful with the assumptions. And he has a section of the book, Corrections to Exponential Decay. So I go through the corrections, and I can read this, but he goes through it and says, the wings of a spectrum go to 0 more rapidly than those of Lorentzian. This results in corrections to the exponential decay, which we now discuss. At short times, the exponential will be rounded and will no longer have a discontinuous derivative at time t equal to 0. And that getting rid of that discontinuous derivative is very important. And he says it appears for very short times that the decay is not linear as it would be for exponential, but it would rather start quadratically. So I'm not telling you anything totally shocking. It was sort of anticipated by Kohn Tanuji, but no one ever gets to this, well, not no one, but it's just rare that people get into it. You have to really be an aficionado on quantum mechanics like Kohn Tanuji to bring that up. And that idea that at short times it's non-exponential rescues the Tunnel Fet concept. So it's kind of major. So now where does that initial parabolic period come from? So if you look, and this is a book by another one of these French masters of quantum mechanics, Messier. He has this figure, which I copied right out of his book. And he says, oh, wait a minute, initially at short times, the probability, this is the growth of probability at early times, it does indeed grow quadratically. The probability of a transition grows quadratically. And so for short times, you do not follow normal Fermi's golden rule. And it actually changes quadratically. It's kind of obvious. If you go back through the derivation, it's there. It's not that exotic. And let's see, and this is more or less what happens is that when the line sharpens enough, so the line becomes sharp, and with later times it becomes sharp, less than the width of the density of states, then you get your normal Fermi's golden rule, okay? And so early times, quadratic, later times, this thing ends up looking like a delta function, and there's your Fermi's golden rule up in at the top. And this answers where the parabolic part comes from, but I have a feeling that there are only a limited number of people in this audience who've actually studied Fermi's golden rule that closely to notice all the approximations and what happens. It is mostly ignored and forgotten, but for us, it's extraordinarily important. So what do we do in the Tunnel Fet to overcome the situation? Suppose we had a sharp quantum level and we're tunneling into a metallic wire. The metallic wire has a constant density of states, is very, very broad, and unfortunately that leads to Lorentzians. So it tells you do not simply connect a wire to your quantum dot. You've got to be smarter than that, okay? What you need is you need to have a limited density of states. You need to, for example, yes, you might have a metallic wire back here, but your final electrical contact has to be through a narrow band metal, okay? And so this is sort of my picture of a narrow band metal, okay, and has sort of a limited bandwidth, and that's where that second lifetime is. Let me erase this. You see tau p, that's the second mystery lifetime that's part of Fermi's golden rule. And so what is the specification? This says to make a successful Tunnel Fet, the final contact to the quantum dot had better be through a narrow band, heavy effective mass, metallic wire, and then you figure out how am I going to do that? And there is a way to do that using molecular electronics, where there's a great success now among chemists to make semiconductors not out of graphene, but out of graphene nanoribbons. The nanoribbons are essentially conducting polymers, like the old-fashioned molecular electronics, except now we have a reason to do molecular electronics. Before, I never could figure out why I should be doing molecular electronics. But now we have a reason, because it's going to, if I engineer it correctly, I'll have a heavy mass, narrow band metal, and that'll provide electrical contact, and that will also help overcome the Lorentzian and give us this initial parabolic period. Now, people often ask me, well, if it's a heavy effective mass, you won't carry enough current, because you remember the third requirement, you have to deliver current. But you have to remember that everything's so small that the propagation of the electrons is ballistic. And when it's ballistic, you get the same conductivity, whether it's a heavy metal or a light metal. You just get the quantum of conductance, and that's sort of the idea, same idea in carbon nanotubes, that you just have to cram as many carbon nanotubes together as you can, and then you get enough conductivity. So we have more or less succeeded here, and we have first defied the Boltzmann factor, and now we have successfully defied Fermi's golden rule, only the naive kind, because Fermi would say, no, I really meant to have that initial parabolic period, okay? Because Fermi was very smart, and he warned everyone that the red curve was just an approximation. It should really be the blue curve. And so that initial period, that initial slower tunneling is very, very essential to make a Tunnel Fet successful. So in effect, we're bringing spectroscopy into electronics, and we're kind of solving the problems as we go along. And so the initial parabolic decay rescues the Tunnel Fet concept. Great. But it also answers a bunch of unanswered questions it's the following. People who do material science and they do spectroscopy, they often come with exponential spectral tails. And these are called Urbach tails. And these have been very puzzling to theoretical physicists since the 1950s. And many crazy models have been put forward to explain why you get the Urbach tails. And I would say maybe you believe in one model, but it would only apply to one material. How come it's universal in all materials? So we better have to have a universal explanation. So what I've just indicated to you is kind of a universal explanation. So let's show some other regimes where this might be helpful. So this is, I think, a repeat slide, but it basically says, yes, you need the heavy effective mass. You need so the final contact has to be made by a narrowband metal wire, okay? Now, oh yeah, and if you do it, it's the recommendation, I'll show you pictures of graphene nanoribbons. You do it, this is, because at the end of the day, it has to be a transistor. So this is what the IV curve of the transistor would look like. You'd get the conductance quantum up here, and it would fall off sharply and would follow the accepted figure of merit, which is millivolts per decade. And the millivolts would correspond to the second lifetime that's in the generalized, the new Fermi's golden rule. Okay, and if you were unaware of this, you'd end up getting Lorentzians. You could never turn the device off. You'd have to use some other more conventional transistor mechanism to turn the device off. So these are the predicted IV curves. And this is where it came from. It came from the quantum dot interacting with the wire. And now we need to realize the wire should be a very special narrowband metal. And this is the original energy level, which is not sharp, which is instead rather broadened. Okay. Now, I said that this is amazingly common in nature and never been satisfactorily explained. So they're very common in condensed matter. For example, every semiconductor, in fact, almost every transparent material, if you look at the conduction band edge, it happens to be gallium arsenide where there's a lot of good data. You have the absorption of the gallium arsenide is minding its own business, and where there should have been a step function because you reached the band edge, there's never a step function. And instead of a step function, it's still very steep, but it's exponential. And the exponential parameter, it's in units of energy, again, or millivolts, like millivolts per decade. And this is called the Urbach energy. And this is for gallium arsenide. I happen to have memorized this. It's one of the sharpest. Gallium arsenide, it's a pretty good material. So it's 7 millivolts per decade. It should be in every book on semiconductors where they have a list of band gaps. They should also have adjacent, the parallel column should be the list of the Urbach energies to tell you how sharp that band edge is. This is the optical band edge, and you see there are many orders of magnitude, so it's over many, many decades. This was never satisfactorily explained. Some people have a model for gallium arsenide, but then it doesn't work for other materials. They have to come up with another model, and so but here's a simple model to explain it. And how important is this? So this is one of my peeves about Bell Labs. I worked at Bell Labs, and one of the most important things at Bell Labs is that optical fibers are very transparent, okay? And so you say, well, obviously there are some ultraviolet transitions. The band gap is very wide in glass. Glass might have a band gap of 9 eV, but if there's a spectral tail, you'll get absorption in the infrared where the optical communication is supposed to be, okay? So if I believed in Lorentzian, and I have this as a homework problem in a class, is what would be the propagation distance in an optical fiber if you truly believed in Lorentzian line shape? And the correct answer, you could go about 1 meter, okay? Now you'd think that with all the theorists we had at Bell Labs, this would be the most pressing problem to resolve is how come if I believe Lorentzian line shapes, my fiber would be useless, whereas in fact the fiber is incredibly transparent. And the reason the fiber is incredibly transparent is that you have the same exponential tail exists for glass. You start at in the ultraviolet at 9 electron volts, and then the exponential tail goes down, 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 and by the time you get to the infrared, there's almost no absorption left. and the glass is very transparent. And without that, you would not be checking your email today or downloading any web pages, because we get to the internet through optical fibers. Okay, so this is kind of important. And now, if you come up with a theory, it better work for glass, which is a totally amorphous material, and work for gallium arsenide, which is a crystalline material. You're going to have a tough time coming up with one model for both. But this simple idea of correcting some of the approximations in Fermi's golden rule seems to resolve this issue. And in this slide, I think it's too many words here, but basically, it says this is the width of our heavy metal. The bandwidth of our heavy metal is this related to tau p, and this controls the initial period of quadratic decay, which finally gives us the exponential line shape. So this is the new feature of Fermi's golden rule coming in. And then there's a prediction for atomic physics. And so in atomic physics, they love to put atoms into cavities. So you put an atom in a cavity, and they call it cavity quantum electrodynamics. Well, the atom interacts with the cavity mode, and initially things are indeed quadratic. So the prediction is, if you look for light coming out sideways in one of these atomic physics experiments, whoops, let's go back. In one of these atomic physics experiments, what it says is that the emitted light should be a non-Lorentzian spectrum. So I've discussed this with atomic physicists, and they said, oh my God, if I do what you say, I have to spend the next 2 years. It's a hard experiment. Because, why is it a hard experiment? You don't do the normal thing, is measure the center of the spectrum, where everything looks like Lorentzian. You have to go way into the tails where you're measuring the very weak parts. And so it's quite a bit of work. But I'm still hoping to encourage them to see this and to recognize this as being kind of a fundamental physics problem. And it's part of spectroscopy, which they're supposed to be good at. So I mentioned that of all the ways of creating this heavy metal, it seems like the most adaptable would be the graphene nanoribbon polymers. This is a new type of semiconductor. It is better than graphene, because graphene is not even a semiconductor. But you make a ribbon of graphene, which for all practical purposes is just a polymer. And they use polymeric methods to synthesize it, but they can do wonderful things. You can mix and match in chemistry. So for example, suppose you're making a polymer like this, and then you switch to a different beaker, which has a different polymer, like the white one, and then you switch to a different beaker, which has a different monomer, I should have said monomer, and now you got a fat section, and then you get a narrow section. And boy, this looks to me like two quantum wells ready to tunnel, and they have the wires connected to them. So you don't have to do it all with graphene nanoribbons, but just think of this as just a very precise form of molecular electronics. It has little to do with graphene and is in the spirit of molecular electronics. So we have, because we're a center, we actually have different disciplines represented. These are some people. So here's our synthetic organic chemist. Here's Professor Steve Louie, a great electronic structure theorist. He tells the chemist what structure will give the right bands that you want. And Jeff Boker is doing the experiments, and I'm just encouraging them all. And so here's sort of an example of many things they can do. For example, they can make a polymer like this, and they can dope it. So in this case, these red things, I don't know if you can see the bees, but they're boron. They can substitute boron for carbon. And what's unusual about this is that, oh, a doped semiconductor. It's a little bit different because it's deterministic doping, that you know the exact position of every dopant because the monomers are exactly synthesized. So the chemist synthesizes the monomer, then he polymerizes it, and he knows exactly where every boron is, because they have, the chemists, they have ways, if they get a low yield, they purify, and they end up getting a high purity of exactly the structure that they want. So they can do this. And these are just different symbols and different names, 13 units wide, 7 units wide of the nanoribbons. And you do SEM pictures. I think I have an SEM picture. So here is an SEM picture. This one indeed is the it's not a semi-metal, it's metallic. This is the metallic band structure, and it's done with edge states. You see a narrow region separated by wide regions, and there's a defect mode at the every time you switch from a narrow region to a wide region, it's like a different band gap. So at the interface, They make a big fuss about the fact that this is a topological state. To me, it's just another interface state, because that's all I needed. I have a series of interface states at every interface, and these are widely coupled electrons, so they don't interact very strongly, so you end up with your narrow metallic band. And so it's very nice that way. And the amazing thing, of course, you can actually see these in STMs, which is totally remarkable. Now, what is the problem here? You look at this, we don't have that much control, we don't know how to manufacture, et cetera, et cetera. So I see decades, maybe decades, I'm sorry, of material science research ahead. When this new type of transistor is not going to happen overnight, unfortunately. I wish it would happen more quickly, but it takes a lot of people working on to get all the bugs out of this and get it all to work very right. So let me wrap up with some conclusions, and that is that to replace the transistor means to defy the tyranny of the Boltzmann factor, and if successful, then you reduce the power consumption or energy consumption of all the electronics. You reduce it by 10,000 times, but in order to do that, we must accept spectroscopy as part of electronics, and we will certainly accept Schrödinger tunneling as the mechanism, but we reject the naive conventional form of Fermi's golden rule. And along the way, it looks like we solved the Erbach tail puzzle. But we have decades of interesting material science work before this can really be manufacturable. So thank you very much for listening.
So I have a pleasure of opening the floor for questions. Any questions for Eli? Yes, Eli.
Oh.
Yes, I was struck by the shape of your lines there, which remind me of what happens also when you do quantum error correction on the state, but also prolong, and via that mechanism, you can prolong the quadratic period probably quite considerably.
Yes, that's a very good point.
Would you repeat a question?
Yeah, I'll repeat the question and try to interpret it. So people who get really serious about how things decay with time, like for example, if you're building a quantum computer, you've got to be really, really serious about this. And for sure, if you had exponential decay, it would be pretty bad. Let me see if I can find a blank slide on which to put that. Okay, so if you had exponential decay with time, and this is sort of fidelity or quality of the quantum state. If you had exponential decay, that means initially you're falling linearly with time. And this is fidelity. I don't know what to say. It's phi or whatever you want to call it, fidelity. Okay, and so that would be pretty bad, because as fast as you can go, the quantum state is deteriorating. But then they're pretty smart guys, so they figure, wait a minute, exponential decay is wrong. And by the way, all the early stuff for the first 10 or 15 years, they always assumed exponential decay. And I got up in the audience and I said, wait a minute, most likely, in fact, it isn't exponential decay, it's much better, and you can be a lot more optimistic. All of you are, I would say, are my quantum computer experts, you're pessimists. You're a bunch of pessimists, because it doesn't decay exponentially. Initially, it's quadratic. And then if you do error correction, it's quadratic again, and then it lasts a lot longer than expected. The lifetime of the quantum states is a lot longer. So this is a reason to be optimistic about quantum computing. The problem this is not the problem in quantum computing. The problem in quantum computing is there's only one algorithm. And so it's a little early to call it computing. But that gets us into a different subject. Other than that last bit, did I faithfully represent your question? Okay, thank you.
All right, thanks, Eli, for the presentation. So I noticed that, so if I was to answer your question, it was the future is more transistors, right? So you have 4 themes. So what is it about the transistor that, is there something special about electrons fundamentally that you really like and that's your favorite?
Yes, that's a very good question. You know, I started very open-minded. Why didn't I just simply reject electrons? And so I definitely believe in being open-minded. But then you have to sort of constrain yourself. And then you say, well, wait a minute. There's this thing about communication within the computer. You have to have communication. And then you go to a computer scientist, and he says, yes, we teach all the students that it's instantaneous. So I said, well, wait a minute, I'm a physicist. It's not quite instantaneous. It has to go at the speed of light. So then I have so many technologies. I have magnetism and mechanics, so many technologies. And why can't I come up with something other than electrons? And the reason is that you pretty much have to go at the speed of light. You have no choice, because for logic you need simultaneity. That is to say, if something is a 1 rather than a 0, it better still be a 1 rather than a 0 after you've gone right across chip. And so then you ask yourself, okay, I have to communicate. I've got to go at the speed of light. What communicates at the speed of light? And there are only two things: light and essentially microwaves. So we're with microwaves. We have clock speeds of multi-gigahertz clock speeds. So those are the only two things that go at the speed of light. And it becomes a constraint. So you go at the speed of light, what is the function of the wires? The wires are waveguides for electromagnetic waves. And so that's why I say we're not going to get rid of the wires, because it's still one of the best communications media, and there's not only two to choose from. So you can choose optical waveguides or wires. That's it. So if someone has another way to guarantee a high-speed propagation or simultaneity across chip, then I can open up the realm of possibilities. So in the center, I had a lot of initial difficulties with my magnetics team, because they said, we're going to communicate by sending the spin. We'll diffuse the spin along a wire. I said, well, the spin doesn't move very fast along a wire. That's like a spin wave. It's like a sound wave. It doesn't. It's like really slow. And then of course they didn't want to be persuaded, but then the breakthrough happened with the spin orbit torque. And they said, now I see. And even though it's magnetic and has spin inside the little black box, there's still wires coming in and out. And then we were both happy.
I'm looking at the time, and it is 3:45 nearly. We're a little bit beyond time. That doesn't mean that we don't want to talk to you more. As a matter of fact, if you would like to spend more time with Eli, you can join us in 12-3005, and at the same time chew on some grapes, cheese, and other snacks that are provided there. So please do come over to MIT.nano third floor large conference room. But before we close, I need to make sure that you have memento of your visit of today. Indeed, we have a pleasure of having very, very few of absolutely remarkable people like yourself come by to give us perspectives on nanotechnology. And we think that we should leave with you your very own piece of MIT.nano. It's a piece of limestone we have chiseled out to the building just so you can have it.
Okay, wonderful. Now, my question is, does it have the name of every MIT graduate inscribed?
Yes, just look very closely. Thank you, Eli.
Okay, thank you.
Thank you.